Welcome back. After introducing the first chalcocyanide solar cell technology, CIGS, we will now discuss the cadmium telluride technology. The first learning objectives of this video is to understand the material properties of cadmium telluride PV technology and how the doping is achieved in this case. Secondly, you will be introduced to the cell structure of cadmium telluride. Finally, the processing methods for cadmium telluride solar cells will be explained as well. We start by taking a look at some of the material properties. Cadmium telluride is a semiconductor that belongs to the chalcocyanide materials, since the element tellurium belongs to the group 6 in the periodic table of elements. This is indicated by the Roman number 6. Together with cadmium, it forms a 2,6 semiconductor compound. Cadmium is a so-called transition metal, meaning that it has a partially filled d-electron shell. Cadmium telluride has a band gap of 1.44 electron volt, which lies very close to the optimum value for the band gap of a single junction solar cell in reference to the solar spectrum. We mentioned that cadmium telluride is a thin film technology. This is possible since it has a direct band gap resulting in a high absorption coefficient. A layer of a few micrometers is enough to absorb all photons with an energy above its band gap. The atomic structure of this 2,6 chalcocyanide semiconductor is a zinc blende crystal structure similar to that of gallium arsenide. Each atom of cadmium has tetrahedral bonds with 4 neighboring tellurium atoms. At room temperature, the lattice constant is 0.648 nanometers. Cadmium telluride material can be grown both P and N-type. It is however very problematic to achieve moderate to high doping concentration in cadmium telluride. N-type cadmium telluride can be obtained by substitutional doping of cadmium atoms by group 3 elements such as aluminium, gallium or indium. These elements have one more valence electron than cadmium, which will contribute to the free electron concentration. On the other hand, N-type doping can be achieved also by replacing tellurium atoms by group 7 elements such as fluorine, chlorine, bromine and iodine. Finally, intrinsic defects in the material also contribute to the conductivity type. A tellurium vacancy, that's when a tellurium atom is missing, will for instance result in more free electrons in the material as a tellurium atom would accept 2 free electrons. This same reasoning holds for an interstitial cadmium atom, which will release 2 extra valence electrons when ionized. P-type cadmium telluride can be obtained by substitutional doping of the cadmium atom by group 1 elements, including the alkali, metal, lithium and sodium. Please note that so far we did not show the entire periodic table, but only the 8 groups on the right hand side of the table most relevant to semiconductor physics. Within this field, the Mendeleev grouping of periodic table is used, indicated with the Roman numbers. The numbering convention by the International Union of Pure and Applied Chemistry, abbreviated with IUPAC, goes from 1 to 18. Both lithium and sodium are in group 1 in the IUPAC numbering convention, which are the alkali metals, but have the same valence electron configuration as elements in group 11. This is why lithium and sodium can be used for P-type doping of cadmium telluride. Copper is a frequently used acceptor element in cadmium telluride solar cells, but it's very important to limit diffusion of copper into other device layers, as this will degrade the performance of the cell. Acceptor atoms on a tellurium site can be, for instance, phosphorus, arsenic, or antimony. Finally, a cadmium vacancy will act as an acceptor type defect because if this cadmium atom was present, it would contribute with 2 free electrons. In the standard cadmium telluride cell design, p-type material is used as the absorber layer. In the next video, we will continue our discussion on cadmium telluride PV technology. We will discuss the solar cell's architecture and the processing methods. So see you back in the next video.